All right. Has anybody got any more homework submissions for homework 7? Today we're going to begin with the discussion of the design project. You have a draft submission of your demand estimation due on Thursday, and so we'll spend a few minutes looking over that and addressing a couple of questions that have come up so far. So that's due on Thursday, and then Tuesday of next week, homework 8 is due. And so this homework assignment that you just submitted, homework 7, it was largely just based on the continuity equation. Each one of those questions was Q equals VA essentially. And in homework 8, most of those questions are just related to Mannings Equation, which we're going to talk about after we spend some time on the design project. So I know it's a lot of assignments back to back, you know, submission after submission, but conceptually there's not a whole lot of variety of different ideas crammed into a single assignment there. So hopefully that makes it a bit simpler. Any questions on the announcements before we talk about the design project? All right. I wanted to draw your attention to the resource I mentioned in class last time. It's posted on MU Online in the folder Design Project Items. And the supplied resource that has water demand reference info. So if we click on that, it should open up the PDF file. And the majority of these are taken from a textbook that I used when I was in school. It's long since out of print. The last version was 1987, but it's got some interesting information there about precipitation and evapotranspiration. Just to give you an idea when you get into what sort of information you should be looking for your town so that you know how much water is needed to irrigate that golf course. I've got a lot of questions about the units of flow on this table 1.2. Let me make it a little bit bigger so you can look at that. All right. So the units here of flow are liter per capita per day. So that means liter per person per day. So you see here it says for domestic use, meaning people's homes, that the average flow demand is 220 liters per person per day. So from the scaled map, you're going to know in a loop what the area is. You know, maybe the area of one of those loops could be 89 hectares. And then from your supplied data, each student has a different figure. You might find that you have the population density for your town maybe would be 10 people per hectare. That would be on the low end of population density. So if your population density was given as 10 people per hectare, then that would tell you inside of this area you have 890 people. So is everybody with me so far? You apply the population density and the given area to find out how many people are living in each of the loops. And then for a table like this, you get an idea of the average flow demand inside of the loop per person. Now it's interesting, if you get a water bill each month, you can see, you know, in the summer most people use more water than in the winter time. This average of 200 liters per person per day is actually a little bit low for some parts of the country and a little high for others. But it's a good ballpark estimate, and it's fine if you just want to use that as your average daily flow demand. There's also a peaking factor that you have to apply, though. And let's go back to the PDF that has the assignment description, because I think I've put the summary table that you need to submit on Thursday. In addition to all of your calculations, you need to fill out this summary table. Okay, so average day flow rate. So residential demand, you'll have a certain number of people there that are reusing a certain amount of water. Liters per day is what that reference was given to you, and you'll need to convert it to liters per second. So let's say that you have 10 liters per second is the flow rate on an average day. And that means through the 24-hour period of the average day, it's 10 liters per second is the demand. Now the peak daily flow rate, does anybody remember what the peak day flow rate is? It's 1.8. And what does that represent? What does it mean? What's the interpretation of what is the peak day? It's the busiest day. It's the day that has the greatest demand. And so this is going to be the average day. It's the ratio of the average day, of the average flow rate on the peak day to the average flow rate on the average day. So let me write that down just so there isn't any misunderstanding. There's the average day, and there's the peak day. Even on the average day, the flow rate is varying over the course of the day. It goes down at night, up during the day, down again, high at night. So if this is midnight, 12 a.m., and this is noon, and we're back to 12 a.m. And so even on the average day, it fluctuates, but there is some average daily flow on the average day. Now I'm saying average twice. I hope that doesn't confuse you, but you're talking about the average day of the year, the average flow rate during that average day. Any questions so far? Okay, so on the peak day, they're using more water. And so, you know, it's lots of flow demand. And we've got 12 a.m., noon, 12 a.m. again. And so the peak day has some average flow rate. This is the average flow rate on the average day, average flow rate on the peak day. And so 1.8, that's the ratio of the average flow rate on the peak day to the average flow rate on the average day. Okay, so the way that you get this field is to multiply that by 1.8. Peak hour. Where is the peak hour of the peak day? That's right here. This is the peak hour of peak day. Now, what you're going to be submitting, actually what you turned in today was a digitization of that flow demand curve, right? If you look at that, actually the peak hour of the peak day, the ratio is probably something other than 3.25, but don't let that trouble you. We're going to be using the digitization of that curve that you did really for the reservoir sizing. It's just, you can take as a given that 3.25 is the ratio of the peak hour of peak day to the average flow rate on average day. And so 3.25, multiply that by 3.25 to get the peak hour flow rate. Don't multiply it by the previous column. Multiply it by the average day. Yes?
Do those same factors also exist for the hotel, shopping mall?
Well, not necessarily, because if you think about water demand at a sports stadium, yeah, it's not the same patterns as residential flow demands. And so some of these I've just blocked out. Let's take, for example, here the food processing plant. You don't apply any peaking factors to the food processing plant because either the food processing plant is in operation, people are there and doing their work, or it's not. You know, it's on or it's off. And so the flow rate is just going to be, you assume that they're in operation when this critical event occurs. Now, the shopping mall, you can use your own reasoning there and find out your own peaking factors for the peak day or the peak hour. I'd be delighted if you put some thought into what you think might be an appropriate way to peak any of these external flows or commercial flows. But some of them probably will be similar to residential demand variation, and some of them will be probably different.
The spreadsheet that we got for Loop 2, we have Loop 2 commercial population.
Yeah.
Then on the summary table, Loop 2 only has a residential.
Let's check that. All right. Yeah, that's a typo. So that is a residential population density. Thanks for noticing that. I knew something was off, but because I made some changes. I simplified this at the last minute. The fire flows here, NFF, this is the first semester that I've just given them as a fixed fire flow. In previous semesters, I've had the students calculate those based on some assumptions of the structure type. But I didn't really find that error. So what David noticed is that for loop 2, it should say residential population density. I'm going to make a note to myself to fix that after class. So loop 2 only has people in it. It doesn't have any commercial enterprises. And let's just make sure if that, yeah, okay. So there's just residential demand there. There's no businesses in loop 2. Now, did I give you commercial and residential for loop 1? Residential and commercial. But loop 2 is just residential. This one? The units? Persons per hectare, yeah. Okay. Do you think they water the golf course 24 hours a day? Why not? Why wouldn't they water the golf course 24 hours a day? Yeah, they're not going to water during daylight hours or when it's bad for the grass. It's wasteful, you know, if it's in the heat of the day. They say you should water at night, which works out good because usually only the blind golfers are golfing at night, right? I heard a joke. Yeah, anyways. It's not the joke isn't about hydraulics enough to even bring it up. So, I mean, put some thought into things like, you know, for the golf course, when that water is actually being consumed. A reasonableness check, in other words.
For basically doing the same thing, like multiplying by a number, we should just come up with numbers, what you're saying.
For what?
For, like, say for the hotel.
For the hotel, yeah.
Okay. So for your peak flow rate, it's not going to be 1.8, but we need to calculate something.
You know, if you just want to take the easy way and not put much independent thought into it, you could use 1.8. But students will get a better grade when they think, well, let's see, in a hotel, maybe they've got some day shift that's doing the laundry, and so maybe the peak factor, you know, like the peaking factor wouldn't be necessarily 3.25 because that afternoon peaking factor, the late afternoon, evening peaking factor is because everyone's doing laundry and showering and dishes all at once. You have more flexibility on everything except for the residential demand to come up with your own peaking factors. But I think the concepts that are behind 1.8 and 3.25 are reasonable concepts as a starting point for everything else.
Are the two peaking factors that you gave us, are those like standard peaking factors that are used throughout the industry?
No, it's not something that I made up. It's a rule of thumb that's mentioned in Water Resources Engineering by Chin. So, I mean, it's a real thing, but I think that usually if you were going to go and do this at a real place, like a town, you'd go to the town next to them and look at their water demand patterns rather than just using a rule of thumb like this to size the pipes. I mean, there would be related data somewhere else that you could use to extrapolate. Yeah. Okay, so that submission will be due on Thursday. And as a reminder, I have office hours tomorrow from 1 till 3 if you want to come and talk to me before that. Did you have a question? No? Okay. All right. So now we're going to be talking about Manning's equation. And Manning's equation is a really useful formula for finding the normal flow depth. Normal depth. So what is normal? Normal is relative, right? A normal day in engineering is just exhausting. You're working your tail off. You don't get enough sleep. You're in this building too much. But normal flow for a channel means uniform flow that's steady. It means that all three of the lines that we're interested in, the energy grade line, the hydraulic grade line, and the channel bed, are parallel to each other. And we talked about that in our last lecture when we were doing chapter 10 stuff. Just one note to point out that on problem 1116, they ask you about a channel slope in terms of a shear stress that's allowable. And so I wanted to point out a formula that's in your book that relates channel slope of the S sub f, technically, slope of the energy grade line, but if you've got normal flow, then that slope is parallel to the water slope and it's parallel to the channel slope S naught in terms of the shear stress. And so shear stress, remember, has units of newtons per meter squared, and unit weight has units of newtons per cubic meter. What about hydraulic radius? Meters, that's right. So shear stress is newtons per meter squared. Unit weight is newtons per meter cubed, and we're multiplying that by hydraulic radius, which is meters squared divided by meters, because it's area divided by wetted perimeter, which is a length. And so that just works out to meters. And then slope of the energy grade line, slope has units of meters per meter. It's talking about the vertical change relative to a horizontal distance. And so slope is unitless because it's meters per meter. And so what we end up with is newtons per meter squared for shear stress. And the shear stress is what's responsible for the fact that the flow depth isn't changing even though the water is going downhill and is gaining energy as it goes down here. As the water goes downhill, it would be gaining kinetic energy because the elevation upstream is being exchanged for an additional flow energy, but there's an equilibrium where that energy is being spent on the resistance that is applied by the bottom of the channel. So if we have steady uniform flow, then equilibrium exists and all three of those slopes are equal to each other. So flow energy equilibrium just means that the resistance, which is the shear stress of this channel bottom pushing opposite the direction of flow, is balanced out by the energy that's gained by the flow as it moves downhill. And so from location 1 to location 2, upstream is location 1, downstream is location 2, there's some delta Z here. You know, the channel incline is such that there's a change in elevation, and that change in elevation is equal to the energy that's lost because of shear stress. Manning's N, which is a roughness coefficient, is sort of an evolution of another formula called the Chezy equation. And I've shown you the Chezy equation previously. And in the Chezy equation, back when it was derived, it was thought that flow velocity could be predicted as a function of hydraulic radius to the 1/2 power. But what Manning showed was that the data, the predictions of flow depth, fit the equation better if hydraulic radius to the 2/3 were used instead. And so slope is still to the 1/2 power in the Manning's equation, but hydraulic radius is to the 2/3. And you'll notice that there is a prefix here of 1.49. Officially it's 1.486. 1.486, yeah. Round off to 1.49 when we're using BG units of, R is going to have units of feet in BG. The slope is unitless. And the reason for this 1.49 is the way that N is measured. N doesn't have any units. I'll show you a table of N in a little while, but the N values that we have are for SI units. And so when we apply those N values into traditional units, we have to use 1.49. And it was thought that that would be simpler than having two different tables of N, a table of N for SI units and a table of N for traditional units. So we just changed the equation slightly instead. And if there ever is a need, you can convert between Manning's N value and the Chesney C value according to this formula. So let's get a little bit of experience looking at N values. This is from a different text. On the next slide are N values from your text. And speaking of text, no, just kidding. The Manning's N value on the low end is smooth surface. And so if an example says, for example, smooth concrete channel, then you'd use the low end of the concrete. And an N value of 0.011 would be very optimistic. That would be like a polished concrete that was extremely level, where at the upper end of that, 0.02 would be a concrete that is has a granular, sort of a gritty surface that would be sort of abrasive to touch. And sometimes it's difficult for natural channels, for like earth-line channels, to know where in this range to go. There's a slide we'll look at in a minute that relates the diameter of the particle that's lining a channel to the N value. But for this example, I'd like you to calculate the flow capacity in terms of Q, so that's cubic meters per second, when you've got a rectangular channel and the flow depth is 1 meter and the width of the channel is 3 meters, and we've got a 1% slope. So since that's defined as a smooth concrete channel, N will be 0.01. The slope we express as in terms of a decimal, 0.01. And then we have a rectangular channel where the bottom width and the top width are both equal to 3 meters. So B equals 3, capital B equals 3 meters. Because it's rectangular, they're equal. And then the flow depth, Y sub N, is 1 meter. Now, the actual conduit may be taller than that, but it doesn't matter to us because the only thing that's relevant for calculating the flow rate is the flow depth rather than how tall the channel goes.
0.011 per N.
That's right, yeah, thank you.
And you said you use the left side for smooth.
Yep.
Right side.
The lower, well, the low range is smooth and the high range is rough. Since it's in the denominator of Manning's equation, that means that if you've got a small N value, that will give you a big velocity. And if you have a big N value, that will reduce the velocity. So what we want to find here, what you need to calculate, is the flow rate Q. The formula for flow rate in terms of Q is that we multiply this formula for V by the cross-sectional area A. And so that makes it Q is A divided by N times the hydraulic radius to the 2/3 power, slope to the 1/2 power. Okay, the cross-sectional area is just going to be the width B times the flow depth Y, and so that's 3 square meters. The wetted perimeter is every place the water's in contact with the side, not including the top. And so there's this 1 meter, 3 meters along the bottom, and then 1 meter along the side. That gives us a total of 5 meters. And so the hydraulic radius is the ratio of the area to the wetted perimeter, and that's 0.6 meters. So we can substitute those into the equation for Q.
How do you get seconds
From the Q,
from velocity?
yeah, it's not dimensionally homogeneous. This is an empirical equation rather than a fundamental equation, and so I guess you could say in theory it's built into the n value, but really since it's dimensionally homogeneous, you don't get consistent units just by looking at what's on the right hand side being equal to what's on the left hand side. Good question. So the cross-sectional area, 3 square meters divided by the n value, 0.011. Hydraulic radius to the 2/3 power, slope to the 1/2 power, and you should get a flow rate of 19.4 cubic meters per second. So on the scale of difficulty, problems where you're asked to find the flow rate are about as easy as they get with Manning's equation. The greater challenge is sometimes finding the flow depth when the flow rate is defined for you. And we'll take a look at one of those in a little bit. But what if they said that you needed to design the channel width in order to convey 30 cubic meters per second? So what we know is that this channel, which is 3 meters wide, carries 19.4 cubic meters per second. So what I'm asking in the second part of this example is, how big should it be? How wide should it be? B equals what in order to have the flow depth still be equal 1 meter, but now we want to have a flow rate of 30 cubic meters per second. Yeah, we're going to have an unknown value for B. So B actually exists in the hydraulic radius formula and the area formula. Sometimes students ask, well, can't we just scale it? You know, this was 3 meters and it took 19 cubic meters per second. Why not just make it a percentage wider? You know, like increase the width by the ratio of 30 to 19.4 times 3 meters. And that gives you the new width. That approach doesn't work because, remember, our flow resistance is a function of how close we are to the surface that's imparting resistance. And so if you make it wider, there's more flow area that's far away from the channel sides, and so it doesn't scale linearly. And so this shortcut approach doesn't work. What we have to do is we have to express Manning's equation in terms of an unknown width B. And so that would be 30 cubic meters per second is equal to B times 1, because that's the formula for area. It's the depth Y times the width B. So this is area divided by 0.011. And then we've got B times 1 divided by 2 plus B. So 2 plus B is the formula for our hydraulic radius. If we've got 1 meter on the side, 1 meter on this side, and an unknown width of B, and that's to the 2/3 power. And then slope, 0.01 to the 1/2 power. So how would you solve that? You could just iterate. You could pick successively greater values of B and find out when does the right-hand side equal the left-hand side of 30 cubic meters per second. Some of you may be able to solve equations on your calculator. And we'll take a look in a little while of a video that Professor Pearson recorded for the Casio FX115 and how to solve equations. He recorded a screen demo for that. For me, I just type it in my calculator and find out that the width B is 4.264 meters. And so that is the width that you'd need in order to get 30 cubic meters per second. And if you substitute that B value in each of the locations where we need to know it, then it works out to 30 cubic meters is the answer. Here in a minute we'll solve this using Excel, and then we'll also go through Dr. Pearson's video that shows how to solve equations in Manning's equation specifically using the Casio. Any questions about this first example? Here's the table that's from your book that's showing Manning's equation. And so you can see that for a finished concrete, they're putting the range of n values from 0.011 to 0.016. And contrast that to the previous table, which I took from a different textbook, where they said concrete was 0.011 to 0.020. So picking the right n value is kind of an art more than a science or something quantitative, and it requires a little bit of experience and observation. People who continually make flow models and go into the field and do surveys of channels will sometimes have tables that they're familiar with and will instinctively assign n values, but at this early stage you can just rely on the book to give you an n value, or if I say that it's smooth, then you'd use the smaller value, and if I say it's rough, you'd use the larger of the range. It's interesting to compare values, though, that when you have channel flow that is going over, like in the floodplain, and it's going over grass, you can see that the length of grass has an effect on the n value, and so a high grass is going to impart more resistance because the range starts for the low end is a higher value, and the high end of the range is higher than the high end on the short grass range. I guess short grass would be mowed and high grass is probably not mowed. I don't know. In the floodplain? There are a lot of people that live in floodplains in West Virginia.
Well, I mean, I guess you
Yeah. You wouldn't mow it while it was covered with water. No. It would probably be mowed before the water got there.
well,
Yeah.
I'll live in one, we have to wait for some time to over that.
Because it's
that's cat.
So this is that equation that I mentioned finally brings a little bit of empiricism to selecting an n value. So if you want to go out and classify the diameter of a channel bed, let's say it's smooth gravel or something, you've got a median particle size of 0.5 inches, then you can find the n value using this equation. Now the problem is that this equation is also just an empirical equation, and so there are going to be exceptions to this. And then the other problem is that usually in a stream, not every particle that's lining the stream is the same size. There's going to be a distribution of particle sizes. And so this is saying the median grain diameter, but the median can have a really large spread. There can be, if we look at a normal distribution, there can be a pretty closely packed normal distribution, or it could be really widely distributed. And that's certainly going to have an effect on whether the n value matches up to what this would predict. And so let's say that the median grain diameter was 0.5 inches. Then in terms of feet, that's 0.5 inches divided by 12 inches per foot. And so the grain diameter would be 0.04167 feet. And so n could be estimated as 0.034 times the 0.04167 feet to the 1/6 power. And so this is 0.589. And so the n value would be 0.02 for a channel that had the median grain diameter of 1/2 an inch. And if you've got big stone cobbles, maybe riprap of broken up concrete, you're going to have a larger n value, because here, the larger the grain diameter, the bigger the n value, but it's to the 1/6 power is what they estimated. The n value increases to the 1/6 power of the grain size.
How did they estimate that with trees?
Well, they probably didn't have trees in the channels that they estimated this for. I think this was probably a channel that was just lined with gravel or sand.
Going back to this thing, your flows, like, kind of like after a flood, you'll have a lot of debris.
Yeah. Sounds like a good research project to find an equation that relates like an old washing machine in a creek to the equivalent Mannings equation, n value. I don't have a table that lists different debris and intensity of debris. Although in West Virginia, that table would probably be pretty useful. At least out by where I live, you've got the tires and washing machines and siding, mattresses, dead bodies. Okay, so trapezoidal geometry continued. We love trapezoidal geometry, right? So we have a channel that has a bottom width of 15 meters. This is the one we did previously. Had a bottom width of 15 meters, and the side slope is 2 to 1. The horizontal component is 2, the vertical component is 1. So let's say we've got 17 cubic meters per second going through there, and we know the channel slope is 0.45%. So what is the depth? Now I've rearranged the equation. This is Manning's equation that we've seen so far. And here's a little trick. Hydraulic radius is area divided by wetted perimeter. So if we combine this area with the area that's in the hydraulic radius, so this is area to the 3/3, this is area to the 2/3, hydraulic radius to the 2/3 is the same as the area divided by the wetted perimeter to the 2/3, which is the same as area to the 2/3 divided by the wetted perimeter to the 2/3. So what we're saying is combine that one with the area that's in there, and so now it's area to the 5/3 divided by the n value, the wetted perimeter to the 2/3, and the slope to the 1/2. Sometimes expressing it like this makes it easier to solve Manning's equation. And then furthermore, what I've done is I've rearranged the equation so that the constants are on the right-hand side of the equation. The n value is given, the flow rate q is given, the slope is known, and everything where the unknown depth is a factor is provided on the left side of the equation, area and wetted perimeter. So let's solve this using Excel. This is the second example using this channel. Yeah, right. So the n value that was given the last time we saw this channel is n equals 0.013. This is from the last class period. Yeah, so that's the n value, and we've got 17.5 cubic meters per second. The slope is given there. So how would we solve this using Excel? We're going to have on the left-hand side of the equation is going to be the area to the 5/3 divided by wetted perimeter to the 2/3. So area to the 5/3 divided by wetted perimeter to the 2/3. And I'm just writing that to remind myself what's going in this column, not that that's the actual formula that's going to be calculating. And then on over here we've got n times q divided by slope to the 1/2 power. Okay, and let me just put in some constants so that we could change it around if we wanted to. We've got n is 0.013 for this example. The slope is 0.0045, and then the flow rate that we are solving in this one is 17.5 cubic meters per second. That's what was given in the assignment description. Q. Boy. All right, so here we're going to have n times q divided by the slope to the 1/2 power. And so we get the right-hand side of the equation that we're going to be trying to get this all equal to. And then we have to also have a guess value for the depth. And so we're going to have some guess value of the normal depth y. And y is going to be in terms of meters. So maybe the depth will be 1 meter. Okay, what is the formula for the area and the wetted perimeter that we're going to be typing in to Excel? You found the table, that's right. We're going to use that, the formula in terms of the T, and so we have to calculate W. Okay, so we know that from the table, W is 1 plus T squared to the 1/2 power. Okay, for us, that is 1 plus 2 squared to the 1/2 power, the square root of 5. So that's 2.2361. Area to the 5/3 divided by wetted perimeter to the 2/3, that's going to be, area is b plus ty times y, and that will be to the 5/3 power. And then down here will be the wetted perimeter to the 2/3 power. So that's b plus 2 times y times w to the 2/3 power. Okay. So I'm going to need another row for the w that I've just calculated, and that is square root of 5. Okay, so the bottom width here, B of the channel, bottom width is 15 meters. And that's all we need. Okay, so in this hand, this equation is going to be the area, so equals B plus T. Oh, I don't have T in. T is the side slope, and that's 2, because we know that the horizontal component of the side slope is 2 for every 1 vertical increase. All right, finally, equals B times plus T times y times y, and that is to the 5/3 power. And then all of that is now going to be divided by the formula for the wetted perimeter, so that is B plus 2 times y times w. And that's to the power of 2/3. Okay. So how are we going to solve this? Anybody have an idea of what my intentions are, where we've got this left-hand side and right-hand side? How have we solved problems like this numerically in the past? You find a difference and then do goal seek. So what's our objective is for the difference to be equal to 0. So I can play around with it manually. 1.1, the difference is getting worse. 1.2, 1.3. I'm starting to think there might be an error in the formula. Let's see here, because that should be getting better as we approach the solution. Let's see here. The n value. Q times n. Oh, I've got the B1, B3, and B2. Okay. $17.5. All right, well, let's just see what we get. That may not be wrong after all. Okay, so we go to data, what-if analysis, goal seek, and our objective is for the difference to be equal to 0. And what we want it to change to find that is the flow depth. So it goes through and finds the flow depth. Oh. Let's start over. Objective is for the difference to be equal to 0 by changing the flow depth. Okay. So let's check that and see if it works out. Okay, so 0.407. Okay, so we've got the B, which was, so Y is 0.407 meters. And hopefully, if I haven't typed any errors into the equation, then what we can do is back substitute everything in, and it'll work out so the left-hand side and the right-hand side are equal to each other. Okay, so it was 15 plus 2 times Y, 0.407, times Y, 0.407, and that is to the 5/3 power. And then the width, 15 meters, plus 2 times Y, 0.407, times W, which was 2.2361. Okay, 2YW, and that's to the 2/3 power. So what we're hoping is that that will be equal to the right-hand side, which was 3.39. So I'll get my calculator and go right along with it. 15 to 0.407 to 2.407 Okay, so in the numerator here is 22.27. The denominator, 15. 2.407. 2.2361. To the 2/3 power. 6.565. And the ratio, 3.392, which is what we were going for. So yes, it does work out. That depth is the correct flow depth. So we solved it using Excel, and we checked it by substituting back into Manning's equation. So we know the flow depth now. We know what flow rate you're going to expect in order to accommodate 17.5 cubic meters per second through that channel.
Calculator you use for your phone.
It's called Droid 48, and it's an emulator of the HP 48 calculator. And it's set in the reverse Polish notation, which I might have told you guys about before, where you're not typing things in with the algebraic order of operations. It's actually a really, it's a really strange way of doing things. Like if you want to multiply two numbers, you don't do 2 times 2. You do 2, enter, multiply. It's like you type in all the numbers and then you do the, and over the long run it saves time, but it takes some getting used to. All right, so just to summarize, what we do is, depending on whether it's an SI problem or a BG problem, we rearrange the Mannings equation so that both of the terms that have the depth are on one side of the equation and the terms that have the constants are on the other side of the equation. We find out what are the area and the hydraulic radius in terms of the depth that will equal the product of all of those constants. And here's the table from your book, table 10.1, that has channel geometry. And you can, depending on whatever the channel geometry is, you can substitute any of these areas, wetted perimeters, and hydraulic radiuses into Mannings equation. Mannings equation is valid for all of them. All right, so here's another problem where we're trying to solve trapezoidal geometry for a flow depth. And how many of you have those Casio 115 calculators? Hold them up if you've got it. Okay, get it out. You're going to go along with Dr. Pearson as he solves this next example using a Casio. And he prepared this video a couple of years ago because, I mean, you might as well teach me Chinese because I'd learn it faster than I'd learn how to use one of those Casio calculators. They just make no sense to me whatsoever. But it's because it's a crazy calculator and it's algebraic mode. So Dr. Pearson took pity on me, and more specifically took pity on the students, because these are hard to solve if you don't know how to type the equation, Mannings equation, into your calculator. And so he goes through that process. So we're going to solve this in just a minute by watching his video, and you'll go through and type while he does it. But here we've got a trapezoidal channel where the bottom width is 3.5 meters. The side slope is 2.5 to 1. And so that means that T is 2.5. Here we have a roughness N value. Mannings N is 0.014. And the flow rate's 29 cubic meters per second. So we're going to try and find out what is the flow rate, what is the flow depth for a slope of 0.1%. So let's just summarize all those parameters that you're going to be putting into the equation once you enter it. The emulator, the computerized emulator of the calculator he has, solves the equation a lot more quickly than your calculator will. But we've got Q is 29 cubic meters per second. Okay, N is 0.014. The slope is 0.001, because 0.1% is 0.1 divided by 100 will give us this slope. Okay, the side slope T is 2.5. And what else have we been given? The flow rate, oh, the bottom width, B. So the bottom width is 3.5 meters. Okay.
In this little video, I want to show you how to use the Casio FX115 to solve Mannings equation for a trapezoidal channel. The equation is given to me by Dr.
Sound working. That wasn't so bad.
In this little video, I want to show you how to use the Casio FX115 to solve Manning's equation for a trapezoidal channel. The equation, as given to me by Dr. Wade, is shown on the screen. In order to use the Casio, we have to do some translations of the variables. We don't have a Q variable, for example, nor do we have a T. We do have a B, C, D, X, and Y, so we'll do some translations here. The equation will be A
I think the video stalled there. Maybe the internet's slow right now. Okay, so let's take the opportunity of the stalled internet just to point out that this is substituting in both the equation for the area. So this is area to the 5/3. So it shouldn't look too unfamiliar. The formula for area is B plus TY, and all of that times Y. So this is area to the 5/3. Square root of S is the same as S to the 1/2 power. And then we've got N, Manning's N value, and then here's the formula for the wetted perimeter for our trapezoidal channel, and that's to the 2/3 power. And so what he's saying is the reason why he has to reassign variables is that the Casio, for example, doesn't have the letter Q on it. There isn't a Q on there. So he's going to say, he's going to rewrite the formula so that A is Q, B is the bottom width, this T, which is the side slope, he's going to assign variable C. The slope of the channel is going to give the variable D, the depth Y is Y, and then the Manning's N value he's going to assign X. So he's translated the given formula into a Casio-ready formula because Casio doesn't have all of the keys for the variable names that we use. So he's going to try and type in this equation in the Math I/O mode, which prompts you to enter in all these variables. Once you type it symbolically, then it'll ask you for the numerical value of each of these variables and then solve for the one that, you know, the comma and then Y is, you're going to be solving this equation where numerical values are given for everything, all the variables except for Y, and that's what it has to find. We'll shoot.
Y, so we'll do some translations here. The equation will be A
I don't know what to tell you. Have you seen it before? Do you remember it from then? Can you solve for Manning's equation using your calculator already? Let me see if the Internet Explorer plays it any better.
The equation will be A equals, notice we got to use the alpha button, and a couple parentheses to make sure operations get done in the correct order. B, which is going to be used to represent B in the original equation. A is being used to represent Q. Plus T times Y, but in this case T is really variable C on the Casio.
Boy, Marshall must not have paid its internet bill this month. I hesitate to take it down out of HD, but I think that maybe...
And Y is Y. Close the parentheses and multiply that again by Y. Close the parentheses and raise all that to the 5/3 power. Since I'm in the Math I/O mode, I can make it look pretty much like the equation in its original form. So I'll put the 5/3 power, hit the cursor control to the right a couple times to get back down on the main line, and then multiply that by the square root of S, which in this case I'm letting D represent S. Hit the right cursor control to get out from underneath the radical, and then divide by the denominator, and I need a couple parentheses to make sure the operations get done in the correct order. Whoops, I only need one to begin with. X, which is being used here to represent variable N, multiply that by left parentheses b plus 2 times y times the square root, and again I'm in the math IO mode so I can make it look pretty much like the original equation, 1 plus c, which is being used to represent t, squared, and get out from underneath the radical, close the parentheses, raise that to the 2/3 power, get out from underneath the, away from the exponent, close the parentheses, and say comma y, which is shift right parent alpha y, and hit solve, which is shift calc. I've already solved this once, so I already had a equal 29. If I hit enter that value again, b equal 3.5, or enter a new value, c equal 2.5, or enter a new value, d is equal to 0.001, x equals 0.014. I'm going to put a starting value in like 0 for y, since I really don't know what the answer is. And when it solves it, it comes up very quickly on the emulator as 1.6577, probably 10 to 20 seconds on your calculator. If I hit shift solve again and enter the same values for everything except y, maybe I'll enter a stupid value like -3 and hit solve, it's going to come up with a negative answer. That simply means that there's another solution, impractical or nonsensical solution, that you need to ignore. So give it a good starting value. Shift calc, put in value for a, b, c, d, x, and for y we'll put in 1 as a starting value. And notice we come up with the right answer.
All right, so I've given you the address to find that video in your notes, and of course it's a video within a video now since it's recorded for today's lecture. And hopefully if you need to play it in high definition at home, you'll be able to get it to play in a way that we couldn't today. Now you're going to need to be able to solve the trapezoidal channel, solve for the flow depth y for the whole rest of the semester. And so this isn't something that you can just hope goes away. You have to figure out how to solve for the depth. It's a must-do because we're going to be using trapezoidal channels not only here in uniform flow, but also when we get to gradually varying flow as well.
Will we have access to Excel exams?
Sometimes yes, sometimes no. You have to be able to solve it with a calculator. You can't depend on being able to do it the right-hand side, the left-hand side way.
What was the advantage of using letters instead of just the values?
The advantage is that if you have it symbolically, then you can change around any of these. You know, if you're asked to do a design, if you were asked to, if you found out what the depth is, let's say when he solved that one just now, the solution was 1.66 meters. So the answer, y is 1.66 meters. So let's say in the second part of the problem, what channel width is needed to get the flow depth less than 1.5? So having it all typed in symbolically would allow you to edit the equation so that now the unknown is going to be b, and then you'd be given y is 1.5. And so it gives you flexibility, is the advantage of using symbols instead of letters. Also, as you're typing the equation, it's a little bit easier to type the equation and not lose track of where you're at if you're using variables instead of the numbers. All right, here's an image of a channel that's in pretty bad shape. This channel is experiencing significant scour, and so a lot of the material is being lost. It's being moved downstream. That's called sediment transport, when the channel is unstable and a lot of mass is being moved downstream. And over time, it will scour all the way to bedrock, and then it'll continue to scour, although it'll be a little bit more slow. So the shear stress equation, which you've already seen today, sometimes is used as the basis for design. Sometimes in a problem statement they'll say that there's some maximum allowable shear stress, and they'll say that based on an analysis of the soil. They'll find out what the cohesive stress of the soil is, and so if you need to use Manning's equation to find out what the maximum velocity is for a stream, then you can rearrange the shear stress equation in order to do design. And let's say, just briefly for example, that if we tested a soil in the lab and found out that it has a tractive force maximum of 10 newtons per meter squared. So what we're saying here is that the shear stress that's allowable is 10 newtons per meter squared, and that this particular material has an N value of 0.02, and we know that the channel slope is 0.015, then what is the velocity that should be allowed in order to prevent that tractive force from being exceeded? We can rearrange the shear stress equation for hydraulic radius. And by doing that, it's 10 newtons per meter squared divided by the unit weight of 9.10 newtons per meter cubed, and the channel slope. And so the hydraulic radius that we should be designing for is 0.0680 meters, and that's what we're going to substitute into Manning's equation. So it's from the maximum allowable shear stress that we find out the hydraulic radius, and then that's substituted into Manning's equation. And so the maximum velocity will be 1 divided by the N value of 0.02. And now we put in the hydraulic radius directly. That's equivalent to this maximum shear stress, and it's to the 2/3 power, and the given slope of 0.015 to the 1/2 power. And when we substitute that and compute it, it's 1.02 meters per second is the velocity that will cause a tractive force of 10 newtons per meter squared. And the interesting thing is that we don't actually even know what the channel geometry looks like. We don't know if this is a rectangular channel or if it's trapezoidal, but that's just a velocity over a surface. It's a velocity over a surface that's causing a certain amount of shear stress. And you'll come to a problem in your homework assignment that asks you to do a similar thing. So that's it for today. If we just take one final look at the announcements, remember that the big thing that you're supposed to be working on to submit on Thursday is this draft submission of your demand estimation. And so please let me know if you've got any questions on that. Have a good day.